Have you changed the new address? Are you still there?
My appointment is going to start at the University of San Francisco on August 25th. So officially, I'm still not still at the client right now.
Okay, that's very precise.
Yeah.
Okay, I think maybe we can get started. So it's my great pleasure and honor to have Mustafa here. And he's currently in Santa Clara University, but I think he will move soon. So he will be going to talk about a unified deep learning framework with high order attention networks. Yeah, Mustafa, please go ahead.
Thank you so much, Kellen, for the invitation. It's my honor to be here. Thank you all for attending. So today I'm going to talk about unified deep learning framework with higher order attention networks. This is a joint work with a large set of people. It is more than one. It's a very large project. Nina Mayolin from the University of California, Santa Barbara, Karthi and Aldo from IBM, Suham and Shreyas from Purdue University, Michael from Aachen University, Ghana Zamzami from NIH, Mitch Roddenberry from Rice University, Tolga from Imperial College, Paul Rosen from USF, and Theo from University of Manchester. If you have questions about this project, please email me. We are excited about this project, and we hope more people are going to join us. So the question that motivates this work is there a general combinatorial framework to define deep learning type computations on topological spaces that preferably that extends current deep learning models on images and graphs? So by topological spaces, of course, we mean discrete topological spaces, so cell complexes, cubical complexes, simplicial complexes, manifolds, and of course graphs and images. So primarily I'm going to focus on cell complexes and another types of complexes that we introduced here, and a generalized hypergraphs as well, called a combinatorial complex. So this is pretty, you're not going to see a lot of definitions in the paper. A lot of it is going to be figures. So I'm going to talk about the word relation a lot. So by a relation, I just mean a subset of the power set of some abstract sets. So I have here some abstract sets, a graph model binary relationships, simplicial complexes model higher order relationships, but you have some geometric constraints. For instance, if you have a relation, let's say this face, then you must have all the edges. So there is this constraint that the simplicial complex has to satisfy. You can loosen those constraints. Instead of having those triangles here for the 2D simplicial complex, you can have more free relations, so that you can have this face. But you also have constraints whenever you have this face. The boundary of this face must be also faces. So that's also constrained on cell complexes. So if you want to remove that, you won't need to go to hypergraphs. So hypergraphs now allow you to have all those. If you look at this relation here between these four vertices, you're going to have this one here, but you can have missing edges. So the structure that we introduced turned out to be very easy to define mathematically, and still retains everything that we need from here. Is called we call it combinatorial complex. So a combinatorial complex, you can think about it as just a set of the power set of the abstract set with a rank function. The rank function satisfies very simple conditions of x. If the cell x, the relation x is contained in y, the rank of x is smaller than the rank of y. You can have smaller than or equal if you prefer. There are functions, but that's it. Just a rank function here, and nothing else. So everything is defined combinatorially. And we showed how to characterize things like cell complexes first and simplicial complexes also in combinatorial fashion. Just remove the topological definition altogether and make it easily implementable. So why should we care? Why should one care at all about higher order complexes? So first of all, from a mathematical perspective, graphs, meshes, images, manifolds are all special cases. So mathematically, one needs to define one model, and this model describes all other models as special case. So there is mathematical elegance into it. From practical perspective, we're going to mention a few ones over here. There are many others. It's really up to your imagination. We're gonna see some of those applications in the talk over here. So many applications based on higher order models, on higher order relations, require flexibility in the nature of these relations beyond the binary relationships. For instance, if you have a set of proteins that interact with each other, then you most likely things are not going to be binary, are going to be just a higher order relation, basically. And that here fits most likely. You're not going to also satisfy. It's not going to also satisfy the relationship that's usually constrained in the cell complex or the simplicial complex. Okay. Expressive power. There has been some work recently on that the hierarchical properties improve the expressive power of the model. So if you are working with model that have more than one hierarchy, you can improve basically the expressive power, and hence maybe the accuracy or the training capability of your model. So data might be naturally supported on higher order elements. So for instance, if you are working with let's say a cloth simulation or a mesh, then your data might not be supported on vertices as it's usually people do with the graph-based models. The data might be supported on edges or faces in that case. So this one here allows, and higher order models also, we're going to see this in this work as well, allow simultaneous processing of signal on various ranks of elements of the domain. So if you have, let's say, data on the vertices for the mesh and on the edges and on the faces, then you cannot use graph-based models, for instance, in that case. You need to go for higher order things. Also, one of the things we're going to talk about today is hierarchical pooling. So if you are, let's say you are giving this graph, and if you want to pool this data to coarsen the signal from the vertices to maybe a skeletonized version of this graph, then you can use the hierarchical properties. So the hierarchical properties naturally corresponds to differential pooling. So these are some of the reasons why one should care about higher order models. Hopefully, going to convince you by the end of this talk that this is the case. Okay, so how are we going to in order to do the introduction for the generalization, I'm going to start with graph neural networks because these are the easiest one to start with, to go for more general complexes. For me, a graph neural network, I'm going to use the message passing model. That's usually general enough. So you have a graph, set of vertices, set of edges, and for every node, you have some data supported on those vertices. So for every this vertex here, I have this HI supported on it, and the message passing model for graph. You look at the neighbors. So you have this vertex here, V1. You look at the neighbors for V1. You have V2, V3, V4, and these vertices send their messages to V1. So that's why you see this vertex V1, the red one, and you have the yellow, the green, and the red one here. They all coming into this box, and that here represents some differentiable permutation invariant differentiable function. Okay, and you can iterate the same thing. So if you iterate from this vertex V4, which is this one, you need to use the adjacency here, which are V3 and V2, and so on. So usually here, you see here this figure here is color coded, which means that its weights here are shareable among those. So this is the same computation function basically that computes all of these. Okay, so this is basically very quick summary for graph-based model, message passing based model. So to go for higher order things, we're gonna start just introducing things with figures. We're gonna in a progressive manner go more complex than this, and I'm going to show you how to build this rigorously. For higher order, now we're going to introduce some higher order relations. So I inserted some faces here. I said F1 and F2. So whenever I want to update the signal on this red vertex, then I'm gonna look at the surrounding vertices, and I'm gonna also look at the edges that I used whenever I am updating these. So here I'm going to look at A2, E3, and E1. So that's why I have these edges here inserted as well as those vertices. And now let's say I want to update the signal on this edge, E2. So now this edge is, people talk about Hodge Laplacian a lot today. So this edge is adjacent to E3 and E5 via the face F2. That's why I have those inserted over here. And I can do the same thing. I can repeat the same thing basically for the adjacency for this vertex here and so on. But again, now since we're talking about the Hodge Laplacian based adjacencies, there are many types of adjacency. You can talk about adjacency, co-adjacency, and stuff like this. So, so I'm going to talk. Let's say if you have a signal on the face, let's say this signal is maybe a vector on the face. So you want to compute you do your inference on the face, then maybe you want to use the co-adjacency in that case. So here the co-adjacency for this face are this pink and gray face. That's why you see them over here. And also I'm using the same edges that are used as a mean of transportation between these two here. So they are co-adjacent via this edge here, these two here, these two faces are co-adjacent via this edge and so on. And you repeat this process. A third one, I'm going to show you, this seems arbitrary right now. I'm going to show you why these are the most natural ones in a little bit. So I can talk about the boundary and co-boundary. So I take, let's say I have a vector field maybe supported on the edges. Maybe I can take the signal between the boundary. So this is the vertices and the co-boundary, which are those faces. And I can repeat the same. Okay, so these are naively, these would be probably a way to define higher order models on simplified complexes. The general equation for message passing is we summarize those. I'm not going to talk in a lot of details about it, but for people who like simples instead of figures, maybe this is a better way to explain things. So this one here, it represents a matrix. I'm going to talk about those matrices in a little bit. This is a some neighborhood relation that defines the neighbors of some other complexes with respect to the complex to the simplex or the relation X. So you have maybe some edge X. And you define NK. So I'm indexing the neighborhood by K because there are so many types of adjacencies. You might have or neighborhood structures. You might have adjacency, co-adjacency, boundary, co-boundary, intersection. It's really up to the user how to define this NK. So the higher order message passing, we characterize it by, it's very similar to the regular message passing. Except you are giving maybe n neighborhood structures. So you're not given just one, which is for a graph-based models, you're just given the adjacency. For higher order things, you might be given multiple ones. It's just up to you. So the first thing that you need to do is to compute the messages between X and Y. This message involves the data that is supported on X, supported on Y, and as well as the X and Y themselves. The reason why we include X and Y here, because the data might not be enough to compute this MXY. Let's say, for instance, if you're doing the boundary things, then the sign between X and Y might be important. So that's why we include X and Y here. Then this one here, for each K, you take an aggregation invariant function, and you sum all those with respect to this K here. So this is for higher order models, you want for each K right now, you obtain this MXK. You want to combine them. We call this merge, and the merge here is a specific feature. We're going to see more intuitively what this means in a little bit. It's a specific feature for higher order models. It doesn't have to be a permutation invariant. It just I mean, you can put let's say your X is a signal on the edge. Then you might want to put more weight on the signal that's coming from the faces, or less weight of the signal coming from the edges, and so on. Okay, so so these four equations here summarize how to do message passing on higher order models. So let me, for people who are not familiar with Hodge Laplacian, I'm going to talk a little bit how to define this neighborhood structure in practice. I'm going to show you also some particular parameterization for those models. So probably the easiest way to introduce things is to talk about the boundary maps. So if I have a simplification complex here, I have 3 faces, 9 edges, and 5 vertices. And then the boundary one basically describe the incidence between the vertices and the edges. So vertices here, I have this is over here, the edges over here. 0 is incident to 0, 1, and 0, 3. Don't worry about the sign here. The sign is there. It's necessary for computations, but it's for the purpose of this talk, it's not important. It's not very important. I only care about that 0, 1 is incident to 0 and 1. That's what I care about here. And the same thing for boundary too. You can define just the incidence between the faces and the edges. Okay. Let's just another example on this simplification complex over here. And the Hodge-Laplacian, this is again, if you are not familiar with it, if you're familiar with it, sorry about the repetition. If you're not familiar, let me just explain it very quickly with this picture. So if I want to I'm going to show you why the Hodge-Laplacian can induce the higher order relation, basically, very intuitively. So if you are at this edge, if you take the co-boundary, boundary 2, then you're going to obtain these 2 faces. Then if you apply boundary 2, this is of course not an invertible function. You're not going to go back to the edge. You're going to go back to the edge, but you're going to also count all the boundaries, for this. And as a consequence, you have computed the adjacencies of this edge over here. Okay, and the same thing for the co-adjacency. This is one here is called L1 up usually, and the L1 down, the co-adjacencies. So you just go the boundary here, the vertices, and then the co-boundary get all the edges that are co-boundary to this vertex, to this edge. Oh, sorry, that you started over here. And so this is a complete example here for people who are going to watch this later. This is just on this particular complex, and the Hodge-Laplacian is basically a summation for all those L up and L down. So if you're talking about up to simplification complex, this one here summarizes all higher order relations. With one of them describe the up, and one of them describes the down. And so the K Hodge-Laplacian generalizes just the graph Laplacian. If you take the 0, 1, it's just the graph Laplacian, and you can interpret the eigenvalues in terms of non-negative frequency. So if this basically gives you a Fourier type, the tools to do Fourier type analysis on higher order models. Okay, so that's from this perspective, this is very quite appealing, and among other applications that other experts mentioned today here. Okay, so I want to describe how to intuitively to give a framework how to send signals across the complex from a machine learning point of view, from a deep learning point of view. So I'm gonna think. So this is just a terminology. I'm gonna define the code chain space. So this is just CI is just so all the complex or the simplices that have, or the cells that have dimension xi, and sorry, this is all the functions that are supported on this. So this is all functions that are supported on, that goes from xi maybe to some r. So maybe, okay. So this one here basically represents data that are supported on the faces. This one here represents data supported on the edges, and this one here represents data supported on the vertices. Okay, so I'm going to use. Let me just erase everything over here. And code chain, I'm going to view it as the data defined on my cell complex or my complex in general. And boundary, I'm going to view the boundary maps as a way to shuffle my data left and right. So the boundary map moves the data from the faces to the edges, and the boundary And boundary one, move the data from edges to vertices, and the co-boundary move data the other way around. So this is also another figure for the same thing. The Laplacian keeps things in their place. So this is just to show you where graphs are. So graphs are basically, so if k here equals to 2. So graph models are over here, basically. I mean, you might want to use the co-boundary, the boundary map sometimes, but the higher order models you might want to use all those other maps as well. Another way for people who like graphs to view this is the Hasse graph. So the Hasse graph is a directed graph whose nodes are the cells in your complex, and whose edges are basically represents deposit structure. So maybe let me just put a very small example. So if you have this very simple complex over here, then the Hasse graph is going to be this directed graph. You have 3 nodes over here, and so this node here represents V1, V2. So V1 here, V2 here, and those edges here represents just the so this one here, the edge, the inclusion relationship. Okay, so the Hasse graph has those. This is the set of nodes for the vertices, the edges, faces, and higher order. So here I have four-dimensional cells, rank cells. So the Hasse graph usually include this edge, those edges, those edges, those edges. However, I just told you that we can go back. So you can define you can define things like, let's say, if you want the adjacency between x3, or you want things that go maybe the intersection between x1 and x3, and so on. So you can think about a nonlinear signal processing, or maybe deep learning model on this as shuffling the data using those edges, basically, on the Hasse graph. You have the Hasse graph, which may be data supporting on some part of in your topological space. Those connections here represents the maps that you defined earlier, that I just showed you earlier, and you might want to shuffle the data around till you do your inference, and that's your inference based on your learning task. Okay, so so this is not how probably you want to actually model the data, but this just gives you an intuitive way how data might be shuffled around using various parts of your hierarchical network and the connection between them. Okay, so how can we describe something like this computationally? So the easier one is the convolution. So if I have some matrix A that's maybe maps this code chain space, the I code chain space to the J code chain space, then this matrix induces a code chain network that goes from the same domain to the same codomain. So this one here, so maybe if you think about A here as maybe just the adjacency matrix, then this one here goes from C0 to C0. And this one here gives you back just the regular convolution. But if you can replace it by anything really. You can replace it by the boundary functions, or you can replace it by the Laplacian and can obtain the same. Okay, so this is a quick convolutional operator, how to define this. And it's, of course, this is equivalent to a message passing induced by the matrix A. So what we to define a general one, so this one here just gives you the most simple one. To define the one that we saw earlier, the one of the picture example that I showed you earlier, we find computation that we need 2 types of operation, and they are actually turn out to be quite intuitive even to code. These are the merge, we call them the merge nets and the split nets. So the merge net is if you have 2 matrices that have the same codomain. So you see here the domain is J in both cases. So you have maybe signal on the vertices, signal on the faces, and you want to combine this signal here to a signal on the edges, say. So maybe this example. Or maybe here, the example here was signal on the vertices, signal on the edges, and we combine these to a signal on the vertices. So this is called the merge operator. So it's very similar to the message passing, except it's a little bit different. So basically, you apply the first convolution here. That's represent the first convolution operator, or maybe the message passing that you have between these two, and this one here, the second convolution, and then you do some permutation invariant function over here. So maybe product summation or anything. The split operation is the dual of that one. So if you have a signal supported on the vertices, on the edges, maybe you want to split it on the vertices and the faces. So here you need two matrices that have the same domain, and maybe they have different codomains. Yeah, so the split operator is basically a dual of that. Now you get the idea. So you can use this operator to build any trivalent graph. So you can start splitting and merging, and you can define a tensor network. And a tensor network is just a network from a tensor of cochains to a tensor of cochains. So to describe the things that we saw earlier, and I told you that these are natural. So you look at this one here. So here you have vertices, and you combine those. So you have vertices here, edges here, and faces here. So what you have here, we combine vertices and edges to vertices. So that's why you have a merge operator defined here, and maybe another merge operator defined over here. And you can choose this map here in an arbitrary fashion. This one, any identity map, maybe identity. So that's the first one that you saw earlier. That's the first one that probably comes to your mind if you think about graphs. So if you want to look at how the signal propagates as you go away from this vertex, so you go from the vertex to the surrounding vertices. You include also the edges, and then you go to the faces and so on. Okay, so this method gives you a way to represent those graphs here gives you a way to represent your higher order model using this graph here. So this graph here basically represents the map. Okay? So instead of thinking about the map in an algebraic fashion or in this notation heavy fashion, you just think about this one here. That gives you summary what this is doing. So let me just erase and then go. So you see here the zigzag going this way. The other zigzag gives you basically the other two ones, the other one that we saw earlier. So if you just look at the zigzag, the other one, it gives you this one, and the other one here, the one that considered the boundary and the co-boundary. Okay, so these are, from this perspective, are very natural. So the other work that have appeared recently by Bunch, I consider basically just put all the connection on this graph, basically, if you realize it using this notation. Okay, we talked a little bit in the paper about discrete exterior calculus, and so I'm not going to talk about this much here, but this framework here can be realized, can be thought about as a basically a way to learn discrete calculus operator. So in roughly speaking, in discrete exterior calculus, you're usually given an operator A that moves some data from I cochain to J cochain. The nonlinear version, you basically add W here on nonlinearity. So you can think about it as basically learning those operators here. I'm going to talk about the learning of the operators A in a little bit. Okay, so this is the Hasse graph I mentioned earlier. This is just a picture for just how the Hasse graph is represented. So to show you a little bit about the attention blocks that we define. And so the attention, we define basically two cases. We have the square matrices case, and we have the non-square matrices case. So for the square matrices, you have some matrix A that goes from CS x to CS of x. So maybe here it goes from the vertices to the vertices. So this one here is not very different from graph attention models. If you are familiar with the graph attention models, this is pretty much the same thing. It's not, there's not much work here, except maybe you replace the matrix, the adjacency matrix A by some higher order Laplacian matrix. And the attention coefficients here, they're just defined to be very similar to what you see in the attention models, the graph attention models. So you define this EIJ, and you just take the dot product between. So you map XS and XSI and XSJ. You concatenate them, and then you multiply them by some tradable parameter AP, and just take the dot product and take the equivalent, and then you normalize with this. If you're not familiar with this, this is not very complicated. It's just what it comes down to. This is just a, let me just explain it like this here. So this matrix here, it has the same shape as this matrix, basically. But every column is a distribution. So every column here represents how much attention this cell has with respect to those other cells. Okay, so just don't worry about the mathematics over here. It's really very it has very simple interpretation. Okay, now for non-square matrices. So now how can you define attention if you have edges and vertices together? So if you have edges and vertices together, let's say that like the boundary, let me show you the picture. So you have this, maybe this edge here, this face 1, 2, 3, and those edges 1, 2, 1, 3, 2, 3, 2, 4, and 3, 5. The easiest way to think about this is using the Hasse graph. So if you look, now you have this simplicial complex and you have the Hasse graph. So now the weights, you can think about them as being supported on the edges of the Hasse graph, which are precisely the non-zero entries in this matrix. So what you learn in this case for non-square matrices here, what you learn is going to be a distribution that describes the attention that those edges have with respect to this space. So that's why you have here, what we have here is kind of you have ST, signal S, and signal T, and we map this to the other way around, to the TS. And the reason for this is that sometimes we use A, and sometimes we use A transpose. Just because we want to define, we don't want only to define the attention of the faces with respect to the edges, we also want to go the other way around. So there is a little bit of subtlety here, and it's not very important for the talk here. When you define the attention coefficients here, things are not symmetric anymore. So if once you want to define the reverse attention, if you are using the same vector over here, then you need to be careful how you invert this, because these might be, they belong to the different dimensions. Unlike the case for a graph where things belong to the same dimension, here things, the XS and XT might belong to different spaces. So they might belong to different Euclidean spaces. Okay, so this is what one particular parameterization. Of course, you can define. You can define also so a higher order attention network. We basically combine all those building blocks. So the building blocks that we have here right now are the non-symmetric and the symmetric ones. So you can combine them to obtain a more complicated model like this one over here. Okay, so probably the most obvious example is to try how this does on autoencoder. So here we put for the vertices, the edges, and the faces, we just put one hot encoders, and we just run very simple model, and we obtain this nice embedding. So here we only the model was trained only on the model never see camels or elephants. It's only trained on something much simpler. So a more serious example, let me skip this one here. More serious examples are mesh segmentation, mesh classification. So for mesh segmentation, we use this particular attention architecture. So you see here, the model output is on the edge over here, and here the model output is on the faces. So this is just because of how the data was given with respect to this particular data. So here, this model here takes feature vectors that are defined on the vertices, on the edges, and on the faces, and give me a label defined on the edges. And this one here takes the same feature vectors basically, and that give me a label defined on the faces. And this is the results here over here. Then the same thing for mesh classification. So one thing worthy to mention, maybe we did not obtain the state of the art of everything, even though we obtain something competitive in everything. But all those models are task specific. So all those models, they are basically built towards, some of them built towards segmentation, some of them built towards classification. This is the same model here that's defined on meshes. They also can be defined on graphs. You can even infer it on point cloud if you wish, if you have appropriate feature vectors. So the also on graphs, we obtain also some competitive results. This is all I have. Thank you so much.
You finished too early. Yeah.
I think I was too fast.
Yeah. So maybe you can go here a bit. So for what you show now, it seems that you have well-defined boundary conditions. So for hypergraph, how do you incorporate that?
Oh, we take the clique graph here.
Oh, so you started with the clique complex for hypergraph and go from there.
Yes.
Okay. And another thing is so recently many people, what this talk is focused mostly about curvatures and curvature-related information. Do you think that somehow curvature can be incorporated into this big framework?
Absolutely, yes. I mean, one thing here, those models, they seem very sensitive to the feature vectors that you choose. Like for instance, here, one of the struggles that we had in earlier, it seems obvious in retrospect, the features we did not choose feature that are like a rotation invariant, and so we had to augment the data to improve the models to the reported accuracy. So yeah, absolutely. If you have, let's say, something like the curvature on a graph is going to be like invariant to so many, especially when you are dealing with the embedded graphs or molecules, stuff like that. Definitely, you can incorporate that on the edges and see what you get. Or on the face, the vertices.
And following up question is more than other than curvatures. Do you think some other maybe geometric information can be involved? They talk about this geometric deep learning, right? And then how the different type of Riemann manifold properties can be.
So I mean, the ones that we chose are very the most obvious ones. So here on the vertices we use the position, here we use the length, and maybe the dihedral angle, and this one here the area and stuff like that. But you can use maybe the eigenvectors for higher order Laplacian over here, or maybe as you mentioned the curvature. Any feature vector, we did not try the other ones like the spectral ones, for instance. I think the spectral one is going to be more robust. But so this is something we have not tried. We did not have to try for this particular study.
And for here, you consider all the different type of topological representations, and it is possible to maybe for example, people talk about a planary graph or some special type of graph that you can have some special design, particularly for this type of problems.
Yes. So one thing that we are, what we did, but I did not report over here, is, so I mentioned earlier, let me go back to this figure, the pooling example. So in the pooling example, what you can do, let's say you want to usually in deep learning on images, you pull before you do the classification, and that's usually have some advantages. So what you can do, maybe you can define mapper. So you can go here and define mapper, and then compute these cells, which are the connected components basically, and declare those to be maybe cells of dimension 2 according to our definition. So and then the pooling operator basically would be what are the incidence between the vertices and those two-dimensional cells over here. So you can pull the signal from the vertices to those signals over here on this one here before. So that this is where topology becomes. You connect this with basically with the classical topology. So you can use mapper to obtain higher order cells, and use those higher order cells as your higher relationships, and then pull whatever signal that you have on the vertices that you have already maybe as part of your input towards your more coarse signal on the mapper vertices, and then maybe do classification or whatever task we're trying to do. Does that make sense?
Yeah, and in this, I was also want to ask about this one. So in these poolings, when you do the iteration, right, the like aggregation, the message passing, and the convolution, do you do that first and then do pooling, or you can do pooling, and after pooling, then you still do this kind of like a convolution?
Pooling actually, you need an operation I did not mention over here. It's called we call it the push forward operation. The push forward is extremely similar to this one, except that you don't. So in pooling, you have, except that you don't have that one. So let me explain. So in pooling, a very simple way to explain it. Let's say you have a signal here on V1, a signal on V2, and you want to pull onto the edge. So you can think about this edge here as maybe the coarsening of V1 and V2. So pooling is different from message passing. Sorry, not pooling. Push forward is slightly different from message passing. Message passing requires two signals. It requires the X signal and the Y signal. So it requires signal on the edge and signal on the vertices to do the message. Push forward only need the signal on the vertices, and that's going to push forward the signal towards this one here, the edge. So what you had earlier for that example, the way you can pool basically is to define B02. So define B02, which represents the relationship between those two cells and those one cells, and then push forward the signal between X0 to X2, basically. That's it. It's very different. It's very similar to message passing, except it requires one signal instead of two signals. I did not talk about this here in details. This is the paper if you are interested. But does it make sense?
Yes. I was trying to see that. Is that after you pooling, right? You end up in this coarse-grained representation, right? Like with like a 5-point. But in this 5-point, can you still do the aggregation again and then like pulling again into a even more smaller one, like multi-scale type of pulling?
Yeah. It's up to you how to define the cells. I mean, these cells. So the way we did it, for instance, we define this. This is a paper we did earlier. Called mapper on graph. We define this mapper on this graph here. We compute those cells, pre-compute them, so the boundary maps are fixed, D02. But you can keep doing that as much as you like in a hierarchical fashion. So maybe you can pick maybe some very at the beginning. Maybe you pick very high resolution, then you lower the resolution as you move on. And this structure, this mathematical structure that we define here, this one allows for arbitrary. So this is where we kind of moved away from cell complexes, because we needed the hierarchy. So here, look at that. Here you need the hierarchy and you need higher order cells. So what's called the hypergraph are not enough. So I need the graph structure, but I also need something supported on the top of that represents higher order relationships. But this is actually where you need particularly this structure and not this one or that one. I mean, this one here mathematically encodes all of these, but it's also for this application, the pooling application is actually required to have something with that flexibility.
I see. Oh, I think other people, you have questions? Yeah, I asked to mention this is very interesting to me. Yeah. Any questions from the audience? Yeah, if you want to ask any question, you can just unmute and then ask.
Sorry. Jin first.
Okay. Yeah, do you all try any like the directed
No.
Oh, okay.
I mean, directions here for us, I mean, as you know, for a hot population, you need that to do the computations, but we did not try direct stuff yet. I mean, we're gonna release the library soon, depending on the people who are, I mean, me and the other ones. We may or may not release the directed version yet, but so far, no, we have not tried it on any data set yet. Good question.
I see. Yeah, because I've seen works whereby they define adjacency for directions, and I think that one maybe there's some other, for example, there's some simplices that they will be filtered out from the, I don't know, from the agency due to the restriction in the agency rule and stuff, and the orientation stuff like that.
Yeah. So I mean, you see here, we mathematically, where is that? I lost that. Mathematically, we thought about it over here, where you have X and Y, but still, this is not we did not do any experiment. We defined it only mathematically. So I would say no to your answer. Sorry about that.
It's okay. Thank you.
Okay, please allow me to ask a strange question. Because the net architecture have a very strong geometric meaning. So do we have any mechanics or scheme to analyze the importance or significance between of the matrix during the training procedure?
Those are higher order models. I would say they are still in their infancy. We kind of put this paper here is one of the we claim to be foundational among other ones that have appeared recently. So the answer is I don't know. I mean, I think that's a research question. Maybe you should go ahead and work on it. Yeah.
Thank you.
A lot of, you start here. That means there is not much that has been done. Yeah.
Any other questions? Oh, by the way, Mustafa, I'm wondering. So for your applications, now you only mentioned about shape characterization of data, special. Is that data in terms of point cloud or is it in terms of meshes? 3D mesh.
The data we tried on in terms of meshes. Although you can, the model, in theory, it can work on non-manifold because you only need the boundary matrices. And it can work on point cloud as well, because you can build the variatorial complex, let's say the VR complex, and then you just attach the feature and then infer. I would not try that yet. In theory, yes, it works on point cloud.
I see. And then how you assign the load vertices and edge vertices properties, the hot vectors on that? Is the angle you mentioned about angle distance?
Well, not using our features. You need to define other features. Not using the features that we define. You need to define maybe spectral features, stuff like that.
But in your examples, the shape characterizations, what are the features you use? You still use other information?
In our example, no, you cannot use those examples for point clouds. You're right.
Mm.
But on point cloud in general, I mean, if you picked your feature vectors from the beginning carefully, then you can train on meshes and infer on point clouds.
I see. I see.
I mean, this is one of the idea here, the one modelness that we mentioned earlier. So you train on one domain and you infer on any other domain.
I see. Yeah.
Provided your feature vectors are meaningful, of course.
Yes. Yeah. Well, maybe one more question. You mentioned about this protein interactions. Have you done something along that line?
Oh, the encoder?
You have a picture of the protein as an alpha helix, and then later, yeah.
This one over here.
Yes, this one, yes. Yes.
So what? I mean, a lot of time you might have a relationship between three proteins, and you might have something like that. So you have a two relationship and you have higher order relationship, but you don't have this one or that one. So you have only something like, but this one here is not a simplicial complex, and it's not a cell complex. So this one here defines a combinatorial complex, the earlier structure. So you can think about it as hypergraph maybe, but you might, the only difference again between that one and is the hierarchy. The hierarchy might be significant. So if the hierarchy is not significant to you, then you can stop here and do your inference over here. But if the hierarchy is significant to you, then you want to include, let's say this one here, the edge structure, and these are higher order relationships. So that's basically what we mean.
I see. Yeah, this is interesting. Okay, I think that's any other questions? Yeah. If not, let's